Welcome to the next session of Strength of Materials. In this session, I am going to start with Macaulay's method. This is in continuation with the introduction lecture that we have already done on deflection of beams. So let's start. Here is a beam AB. At point A there is a reaction VA. At point B there is a reaction VB. This VA and VB can indicate a hinge and a roller support. At C there is a load W1 in the downward direction. At point D there is a load of W2 in the downward direction. The total length of the beam is L. The portion A to C distance is given as A, C to D is given as B, and D to B is given as C. Now for ease of solving this problem, what I'll do is I'm going to just assume this value of A as 1, B as 1, C as 1. I'm not assuming W1, W2. I'll write in terms of W1 and W2. Now, what is Macaulay's method? Macaulay's method basically says that you are going to divide the beam into parts. Now, how many parts depends on the number of points at which the load and support is given to you. So, here I can see A to C can be one part, C to D is another part, and D to B is the third part. So, I'll be dividing the beam into three parts. I'll be writing the equations, specifically the moment equations for all three parts individually, and then I will sum them up and I'll write the equation for the entire beam. Now the first thing that I'm supposed to do is I'm going to draw another diagram wherein I'm going to hold something which is called as a slider. So first I'll draw the diagram, then I'll explain. Every time you solve the numerical, you are supposed to draw the FBD and you're supposed to draw this diagram as well. Now here I need not draw the FBD because VA and VB is given to me. Had it been a hinge and roller, I would have substituted with VA and VB and I would have shown a FBD. So I'm not doing that here. I'll directly start with drawing the beam. This is point A. The reaction here is VA. At point B, the reaction is VB. Now the value of VA and VB can be calculated by using equilibrium equations. Summation of force in y direction is 0 and summation of moment about any point on the beam is 0. At point C there is a load W1. At point D there is a load W2. Now this distance is 1, 1 and 1. That is what I have assumed. It could be any other value. Now what is this concept of slider? I am going to assume that there is a slider, which is my pen over here, and it is going to slide from the end A to the end B. It is free to move. There is no constraint in its movement along the x-axis, if you can observe. So let me assume that the slider is here. Then I'll be actually calling the slider as xx. So when I hold the slider xx, this distance will be x. When I slide ahead, this distance will now become x. And when I slide ahead, this distance will be x. X can start from point A, the slider, which will be 0 when I hold the slider here. When I hold the slider at point C, the value of x will be 1. When I hold the slider at D, this distance is 2. And at this position, the slider will have value 3. But in between, it will be any random value x. There is a rule for drawing the slider on the beam. For a point loaded beam, here you can see there is no UDL, it is just a point load on the beam. So the slider has to be drawn on any one extreme end of the beam. Either you can draw on the portion A to C or on the portion D to B, but never draw it on portion CD. I'll explain why. So here will be my slider XX and this is the distance, maximum distance to be measured from the other end will be x. If this distance is 1, the distance of C from the slider will be x minus 1 and the distance of D will be x minus 2. So this is how the diagram is supposed to be drawn for Macaulay's method. Now what I am supposed to do is I can calculate VA VB using a very simple equation. Summation of force in y direction is equal to 0. Upward force will be considered positive and summation of moment about any point is equal to 0. I can assume clockwise as positive. When I use these two equations, I'll get the value of VB, VA. Now it is obvious that W1 and W2 will be given to me. So I can calculate these two unknown. Next, what I am supposed to do is, I am supposed to write an equation for Macaulay's method using the moment curvature relationship. We know the moment curvature relationship is M is equal to EI d square y by dx square. If you observe, the beam is going to bend something like this. If the beam bends like this, obviously the bending is going to be different at various values of x. So the moment is generally calculated over x. So this is the equation that I have written. Next, I am supposed to write individual equation for AC, CD and DB. So I'll first start with A to C portion. When I hold the slider here, this distance will be x, not this. So when I stand here, the VA will turn in this direction. So it is clockwise and the distance is x. So I'll write the equation as VA into x. Now if you want, you can also assume that the slider is still here and I'm turning VA towards the slider. So it is VA into x. Otherwise, if the slider is here, the distance will be VA into x again. So actually it is VA turning towards xx. So you need to understand that though I am writing for an individual portion, ultimately the whole beam has to be considered for calculating the deflection. Now, VA into x, when I write for the beam A to C, my domain will be from 0 to 1, from 0 to 1 if you observe. So I'll write down over here, this is for A to C portion. This equation will be valid. When I have to write for C to D portion, apart from this VA into x, there will be one more term which comes into picture, that will be this W1 turning towards xx. This W1 will turn in this anti-clockwise direction. My direction is going to be clockwise positive. So here only for C to D portion, I'll write minus W1 into this distance is x minus 1. So I'll write x minus 1 over here. Domain will be from 1 to 2. So this is for CD portion. Now there will be a question definitely in your mind as to why I did not write W1 for AC and I didn't write W2 for CD. The reason is, when you substitute over here, if you observe, W1 will be from 1 to 2. But this W2 is in the zone of dB. It is not in the zone of 1 to 2. Its effect will be seen on D to B portion. So I will only write W1 for CD and I'll only write VA for A to C. Next, I'll calculate for DB portion. Only for this portion, there is only one load to be considered, W2 turning towards XX. So I'll write down it is anti-clockwise, so it will be minus W2 into X minus 2. The domain is from 2 to 3. So this is for DB portion. But when you write the equation of Mx, it is actually EI d square y by dx square. I'm actually going to club up all the three equations. So this will be equal to VA into x from 0 to 1 minus W1 into x minus 1 from 1 to 2 minus W2 into x minus 2 from 2 to 3. So this equation is called as moment equation, and this equation is the first part of solving this problem. The way I have solved over here by dividing the beam into three parts, this is what Macaulay's method is. This is what you will find unique to Macaulay's method. As I have told you in the previous lecture, there are two more methods which you can use, double integration method and superposition method. In those two methods, this kind of division of beam is not done. So this is very specific to Macaulay's method. Now, once I obtain the moment equation, I am going to integrate this equation to find the slope equation, and integrating again, I will get the deflection equation. Generally, when questions of this chapter is asked in any examination, you are supposed to calculate the slope and deflection which occur on the beam. So when I know this equation, I can integrate twice. So I'll just write down over here, integrating twice. When I integrate for the first time, I will get theta. Now on this side, it will be EI dy by dx, because once you integrate, these two are constant, so this gives you dy by dx is equal to, here it will be VA into x integrated, it will become VA x square by 2 from 0 to 1. Next, W1 is a constant term, so x minus 1 integration will be x minus 1 square by 2, substitute from 1 to 2, and finally the last term will be minus W2 into x minus 2 square by 2 from 2 to 3. So this is my second equation, which we called as the slope equation. Now there is one more term which you need to add over here. When you integrate, you always obtain a constant of integration which is supposed to be considered in this chapter. Now generally when we solve integration problems, we tend to write the constant of integration at the end. But in this problem, you always have to write the constant of integration at the start. I will explain you the reason when we solve the numerical. As of now, just take it down that you always need to write the constant of integration towards the front end. When I integrate this slope equation, I'll get the deflection equation. So I've already written integrating twice. So I'll just write down, when I integrate this, I get EI dy by dx will become y is equal to, obviously there will be another constant of integration, so I'll write it as C2. When I integrate C1, I'll get plus C1x. Next term will become plus VA x cube by 6 from 0 to 1 minus W1 x minus 1 cube by 6 from 1 to 2 and minus W2 x minus 2 cube by 6 from 2 to 3. This equation is my deflection equation. So here I have obtained three equations. You can see first is a moment equation, next I have obtained the slope equation, and third I have obtained the deflection equation. In these equations of slope and deflection, if I substitute a particular value of x, I'll be able to calculate that at a particular distance what is the value of slope and deflection on the beam. So this is how Mccallis method is to be solved. Next, I want to take up another important part, that is, on a beam you can also have a moment which comes into picture. So the topic is bending moment equation by Mccallis method, where the beam is subjected to bending moment m. So here is a beam AB, there is a reaction VA and VB, length of the beam is L. At point C, which is at a distance of small a from the end A, there is a moment m which is acting. Now how am I supposed to write the equation when a moment acts? It is very important. So I'll draw the diagram. This is my beam AB. At point A there is reaction VA, at B there is reaction VB. This is my point C. Here there is a moment m. Now at this end of the beam C to B, I'll draw the slider as I had drawn for the previous one. The distance over here will be x. Since this distance is a, this distance will be x minus a. Now I'll directly jump to writing of the equation. Mx is equal to EI d square y by dx square. Okay, this is the base equation. Next I am going to write the equation for the portion A to C. This VA will turn clockwise, so I'll have VA into x. Okay, let's write down the domain. X is 0, x is A, and say x is L over here. So I'll start with 0 to A. This is for A to C portion. For A to C, I'll only have VA coming into picture, not the moment M, because it is exerted at point C, so its effect will be seen on the portion C to B. Now when I go to the portion C to B, I'll have this moment coming into picture. Now this is very important. Moment itself is in kilonewton meter, assuming this moment is in kilonewton meter, which is force into distance. So here I should only be writing moment M between the domain A to L for CB. But this is not the way of writing. There is something different that you are supposed to do. Rather than writing this, what is exactly written is M into, it is exerted at a distance x minus A from the end xx. But if you observe, this itself is in kilonewton meter and the distance is also in meter. So the total value will become kilonewton meter square, whereas this term is only in kilonewton meter. Hence, I cannot write this as x minus A. But I also need to introduce a distance, otherwise in the next equation, the distance of moment from the xx direction will be lost out. So how it is written is, you just add a 0 at the top, which means you raise it to the power 0. Any term raised to the power 0 is 1. So this term is there and also not there at the same time. You can observe that in the moment equation x minus A is introduced. When integrated in the slope equation, this will come into picture as x minus A, and in the final equation of deflection also it will be x minus A square by 2. But when I talk about the moment equation, x minus A raised to 0 is technically 1. So I'll write the domain as A to L, and this is for the portion C to B. So this is how you write the equation. So in all, if I have to write the equation, mx will be ei d square y by dx square will be va into x from 0 to A plus, okay, this is clockwise, so it is plus m into x minus A raised to 0 from A to L. So this equation is my moment equation. This is very, very important because here you write this term x minus A raised to 0, which is introduced in the moment equation as a negligible term 1, but in the slope and the deflection equation this becomes a very significant term. So with this I end this session. In the next session we will start with numericals on Macaulay's method. I hope you have understood this session. If you have any doubts, write to me in the comment section. See you in the next session. Thank you.